Hello there, welcome to Science to Sleep To. I'm Madeline Rowe, and this evening we'll be diving into a quiet little case file about the sky. In this one, we're simply following sunlight as it moves through air. If you are listening with your eyes open at any point, please don't look directly at the sun. If you want to notice halos or sundogs safely, it helps to let a building, a tree, or a rooftop hide the sun itself. For now, you can let the whole scene stay gentle and dim, like a memory of daylight rather than the glare of it. This episode is dreamy on purpose, but it is still hard science, because the sky can be soft and precise at the same time. Back in my office, I switch on the desk lamp and the light hits everything at once. Glass paperweight, a half-empty water tumbler, the beveled edge of a picture frame, splitting into quiet, unexpected seams of colour that slide across the blotter like evidence I didn't file. Outside the window, the city air looks ordinary, but I know better now. The same white light that makes my office feel solid and simple is always carrying a whole spectrum, just waiting for the right angles, the right surfaces, the right tiny crystals or droplets to coax it into view. So tonight, I let the room become a small weather system of its own. Prisms and panes, reflections and soft halos around every bright thing. And I open the folder marked atmospheric optics as if it's a skylight I can tilt just enough to let the hidden geometry of sunlight spill in. Here is the simple premise. Sunlight is white, but white is not one thing. White light is a bundle of colours travelling together, and when that bundle meets certain shapes in the atmosphere, the colours separate and gather, and paint patterns at very specific angles. Those shapes can be round, like raindrops, or they can be angular, like tiny ice crystals floating high in thin cloud. Water droplets tend to make rainbows. Ice crystals tend to make rings, arcs, bright side suns, and pillars of light. And the calmest part of all is this. You do not have to chase these phenomena. You do not have to force them. You only have to understand what the sky is doing when it decides to show you one. We'll start with the most familiar shape. A rainbow resting on rainfall like a slow signature. Refraction, dispersion, reflection. Those three words are going to drift through the whole hour, not as a test, more like a lullaby, a small rhythm of physics that the atmosphere knows by heart. In ordinary air, light travels in straight lines, but when light crosses from one material into another, it bends. That bending is refraction. The amount of bending depends on the refractive index of the material and on the angle the light arrives. Now the gentle twist. Different colours bend by slightly different amounts. Violet bends a little more than red. That spread of colours is dispersion. A raindrop is almost perfectly round. It is a sphere of water with air around it. So a raindrop is like a tiny lens and a tiny prism at the same time. And when sunlight enters it, the light refracts, disperses, reflects inside, then refracts again as it leaves. A single raindrop can send light in many directions, but not all directions are equal. For the primary rainbow, there is a special direction where many rays bunch up, and where rays bunch up, brightness appears. Let's place the scene gently. The sun is behind you, rain is in front of you. The rainbow forms around the anti-solar point, which is the point in the sky directly opposite the sun. It's the place your shadow points, if you can see your shadow. The rainbow is not actually over there, like a solid object. It is an angle. It is geometry drawn by light. It is what you see when countless droplets send a concentrated fraction of light back toward your eyes at a very particular spread of angles. For the primary bow, the most concentrated light arrives at roughly 42 degrees from the anti-solar point. Red tends to appear near the outer edge of that bow, close to about 42 degrees. Violet appears slightly inside, closer to about 40 degrees, and the other colours arrange themselves smoothly between. If you could see the full geometry without the ground in the way, the rainbow would be a circle. From an aeroplane, you sometimes do see more of that circle. From the ground, the horizon cuts it into an arc, not because the rainbow is incomplete, but because your view is. Now we can slow the physics down until it feels like slow motion. A ray of sunlight approaches a droplet. It crosses the boundary from air into water and it refracts. The different wavelengths separate slightly as they bend. The ray travels through the droplet, reaches the back inner surface and reflects once. Then the ray travels back toward the front of the droplet. It exits from water back into air, refracting again. That second refraction increases the separation of colours, and some of those outgoing rays leave the droplet in a direction that is just right to reach your eyes. The reason the rainbow has a bright edge is not magic. It is a kind of traffic jam of light rays. Around that 40 to 42 degree direction, the deviation angle changes slowly with the incoming angle. So many slightly different incoming rays exit in nearly the same outgoing direction. Many rays, similar angles, brightness. That is the whole secret of the bow. Not one droplet doing something special, but a vast population of droplets doing the same ordinary thing, and your eyes collecting the angles where the light happens to concentrate. The sky also has a softer region inside the bow. The area inside the primary rainbow can look brighter than the area outside it. That is because more rays emerge into that inner region for the primary path. So the rainbow is both a coloured edge and a gentle change in background brightness. If the rain is fine and uniform, the arc can be crisp. If the droplets are large, the colours can look bold. If the droplets are small, the bow can look paler and wider. All of that is still the same geometry, just with a different softness at the boundaries. And sometimes, if conditions are just right, you see extra faint bands tucked inside the main bow. Those are supernumerary bows. They come from the wave nature of light, from interference between closely related paths through the droplet. It is still the same sky, simply revealing a finer layer of detail. But we don't need to linger there. We can keep to the broad, calm arcs, because there is another bow that sometimes rises above the first, like an echo. The double rainbow begins the same way. Light enters the droplet and refracts. The colours separate. But inside the droplet, instead of reflecting once, the ray reflects twice before leaving. Two internal reflections change everything. The outgoing rays concentrate at a different angle, typically around 50 to 53 degrees from the anti-solar point, and the order of colours reverses. Red appears on the inner edge of the secondary bow, and violet toward the outer edge. The secondary bow is also dimmer. Each reflection inside a droplet loses some light, and the spread of outgoing directions is broader for that two reflection path. So the light is both reduced and distributed, which makes the bow fainter. Between the primary and secondary bows, there is often a noticeably darker band. That region is called Alexander's dark band. It appears because the primary rainbow sends more light into the region inside its bow, and the secondary sends more light into the region outside its bow. The space between gets comparatively fewer rays, so it looks dimmer. If you ever want a quiet way to measure the geometry with nothing but your body, you can. Hold your hand at arm's length and spread your fingers. A fist is roughly 10 degrees. Two fists make about 20 degrees. and the primary rainbow sits a little over 4 fists from the anti-solar point, if you count carefully and calmly. But you do not need to measure it. You only need to notice that rainbows are angle locked. They stay in the same place relative to the sun and to you. When you move, the bow moves with you, because it is tied to your line of sight and that anti-solar point. And that idea that these are not objects but angular patterns becomes even more soothing when we leave raindrops behind and drift upward to the high, cold air where ice crystals float. Up there, the atmosphere changes character. The cloud is thin, the light is cleaner, and instead of spheres, we have prisms. Ice crystals in cirrus and cirrostratus clouds are often hexagonal. They can be plates, like tiny dinner plates. They can be columns, like slender pencils. And each one behaves like a small piece of optical glass, refracting and reflecting light in patterned ways. The most common halo is the 22-degree halo. It is a ring centered on the sun, with a radius of about 22 degrees. If the moon is bright enough, you can see a similar ring around the moon. The same physics, just a quieter light source. Here is what sets that angle. Light passes through the side faces of a hexagonal prism. For a range of incoming directions, the outgoing direction varies, but there is a minimum deviation angle, where the bending is as small as it can be for that path through the prism. Near that minimum deviation, rays cluster. They pile up in angle space, and the sky brightens into a ring at roughly 22 degrees. That is why the inner edge of the halo can look sharper, like a boundary where brightness suddenly begins. The 22-degree halo often shows a hint of colour. Red tends to appear on the inner rim. Blue is usually washed out, scattered into the background. So you get a warm, pale ring, like a whisper of spectrum. The 46-degree halo is larger and rarer. It is a bigger ring, also centered on the sun or moon, at a radius of about 46 degrees. It tends to be fainter because the conditions and ray paths that feed it are less generous. When it appears, it can feel like the sky has expanded. Now we can add a gentle detail that changes the whole scene. Ice crystals do not always tumble randomly. Sometimes they align, especially plate-like crystals, which tend to fall with their flat faces nearly horizontal, like slow leaves. And when many plates align, the halo can grow bright spots at the left and right of the sun. Those bright spots are sundogs, also called parhelia. They usually sit at about the same angular distance as the 22-degree halo. They can show warm colour, often brighter and more concentrated than the full ring, and they are a signature that the high cloud is full of flat plates holding steady as they fall. If the sun is low, sundogs can be especially vivid. As the sun climbs, their shape and placement can shift because the geometry of refraction through those plates changes with solar elevation. But the calm truth stays the same. The light is selecting angles, and your eyes are reading the selection. There is a whole family of arcs that can appear around the 22-degree halo. Tangent arcs that touch the halo at the top, when columns or plates have preferred orientations. A bright, smile-like arc overhead called the circumzenithal arc, sometimes described as an upside-down rainbow near the zenith when the sun is fairly low. These are all variations on the same idea: shape, orientation, refraction. And then there are phenomena that lean more heavily on reflection. Light pillars are the perfect example. A pillar can appear as a vertical column of light, extending above, below, or through the sun. You can also see moon pillars, or pillars above bright streetlights in cold air. The pillar forms when light reflects off the flat faces of plate-like crystals. If the plates are roughly horizontal, they act like a field of tiny mirrors. Each mirror sends a glint in a slightly different vertical direction because the plates wobble gently as they fall. The result is a smeared vertical line of reflected light. Sometimes, instead of a pillar, you see a faint white ring or band that runs through the sky at the same elevation as the sun. That is the parhelic circle, which can be produced by reflections from vertical faces of ice crystals. It can carry bright spots and subtle structure along it, depending on what the crystal population is doing. It feels like the sky has drawn a compass line. At this point, it can be soothing to notice how different the rainbow and the halo are, even though both come from the same sun. The rainbow is centered opposite the sun, around the anti-solar point. The halo is centered on the sun itself, or the moon. Rainbows belong to droplets in front of you, with the sun behind you. Halos belong to high ice in the direction you are looking, with the sun somewhere in that same half of the sky. Rainbows are typically bigger, about 42 degrees in radius. The common halo is smaller, about 22 degrees, and once you learn those centers, your brain can sort them with almost no effort. If you ever see a small ring very close to the sun or moon, only a few degrees across, that is usually not a halo. That is more likely a corona, produced by diffraction through tiny droplets or ice crystals of similar size. Coronas are delicate, and they sit tight around the light source. Halos are broad, and they live out at 22 degrees and beyond. We can keep the rest of this as slow observation, a gentle walkthrough of skies that change hour by hour, with physics quietly repeating behind the scenes. And if you fall asleep anywhere along the way, the sky will continue without you. Let's return softly to a post-rain afternoon. The air smells clean. The rain has not fully stopped, but it has become fine, like threads. The sun breaks through a gap behind you, low enough to make angles generous, and somewhere ahead, droplets begin sorting sunlight into colour. The primary bow appears first, red on the outside, violet on the inside, every droplet contributing one narrow slice of the arc, depending on its position relative to your sight line. If you shift a step left, the droplets that serve your eyes change. The arc stays anchored in angle, but its material is replaced. New droplets, same geometry. The rainbow is rebuilt continuously, like a quiet algorithm running in rain. A faint second arc sometimes forms above it. Two internal reflections, reversed colours, and between them, Alexander's dark band, a calm stripe of lower light. Now, the shower moves on. The low cloud breaks, and high, nearly transparent ice haze drifts in, almost unnoticed. The rainbow fades with the droplets, and the halo family begins with the crystals. First, a soft ring around the sun, wide enough that you can measure it with your hand, a radius of about 22 degrees, which is roughly 2 fists held at arm's length. A pale circle, sometimes with a warm inner rim. If the crystal population is random, the ring is smooth. If plates are aligning, you begin to see brighter patches left and right. Sundogs, like quiet companions travelling with the sun. They are not separate suns, of course. They are concentrated refraction, a preferred path through a preferred orientation, a bright spot at a fixed angle, made from countless tiny prisms falling steadily. And if you relax your gaze, they can look almost still, even as the cloud itself moves. If the air is very cold and the plates wobble just enough, a light pillar might extend upward, a vertical line through the sun or above it, like a slow brush stroke. Reflection doing what reflection does best, turning a single bright source into a stretched column. And if the sun is setting, the pillar can take on warm colour, because the light is already filtered by the long path through air. It is all the same light, the same star, the same atmosphere, only the shapes have changed. To keep the physics anchored, we can return to the idea of angles one more time, but in the gentlest way possible. A rainbow is an outgoing cone of light at around 42 degrees from the anti-solar point. A 22-degree halo is a ring of light around the sun at about 22 degrees. A sundog is a bright concentration along that ring, usually at the same distance, left and right. A pillar is a vertical smear of reflected glints. You can fall asleep on those shapes alone. Cones and rings, brightness where rays cluster, dimness where rays do not. Now we can slow further and take a longer walk through the atmosphere as if we are travelling upward in layers. Near the ground, the air is dense and busy. Droplets form, collide, merge and fall. Rainbows are born here in ordinary weather, and if the droplets are behind a curtain of cloud, the bow can be muted. Higher up, the air is colder and water prefers crystal shapes. The cloud becomes wispy, and optical phenomena become cleaner because the particles are more uniform and the background sky is often darker. Halos live here. A thin veil of cirrostratus can cover the whole sky. If you hide the sun behind an edge and look for it, the ring may reveal itself. It is not always obvious at first. Sometimes it appears only when you relax your attention and stop demanding it. And that, too, is physics. Your visual system is tuned to edges and contrast. Many halos are faint and broad, so when you stop forcing focus, you start noticing the gentle gradients that were there all along. If the halo is bright, you might notice a darker region inside the ring compared to just outside it. That can happen because rays are being redirected into the ring and beyond, leaving the interior slightly less bright by comparison. It is not as dramatic as Alexander's dark band, but it is the same general idea. Brightness is a bookkeeping of ray paths. The 22-degree halo is often the first clue that a weather change is on the way. Thin cirrostratus can arrive ahead of a warm front, so a halo can be both beautiful and informative. But we don't need to turn this into forecasting. We can keep it as a quiet catalogue of light, a slow, calm list of what sunlight does when it meets air, water, and ice. Let's linger on sundogs for a little while, because they are one of the most satisfying clues the sky gives you. Sundogs often appear symmetrically, one to the left, one to the right, and they tend to sit on a horizontal line through the sun. That symmetry is telling you about alignment. Plate crystals fall like tiny saucers. Their flat faces prefer to stay close to horizontal, so the refraction path through side faces becomes a repeated pattern across many crystals. The result is a stable concentration of refracted light at about 22 degrees. If the sun is low, the colours can be more apparent. Warm tones near the inner side, a pale extension outward. The exact look depends on crystal size, thickness, and how tightly they are aligned. A small detail can make this feel even more real. The refractive index of ice is around 1.3 in visible light, give or take. That's enough to bend rays through a prism path that produces the minimum deviation near 22 degrees, so the angle is not arbitrary. It is a fingerprint of ice, a signature of hexagonal geometry living in the sky. Now let's let that signature soften and spread into a wider meditation on circles. The rainbow is a circle around the anti-solar point. The halo is a circle around the sun or moon. The parhelic circle, when it appears, is a circle around the sky, fixed at the same elevation as the sun. and your own horizon is another circle, a boundary of visibility. It can be soothing to think of the atmosphere as a place where circles are constantly trying to appear. Not because the sky loves circles, but because angles and symmetry make circles the natural shape of light around a center point. When the center is defined and the angle is fixed, the geometry completes itself. If you listen long enough, the physics starts to feel like a quiet walk in a museum. One exhibit is water, one exhibit is ice, one exhibit is your own line of sight, which quietly decides what you get to see. And because this is a sleep story, we can revisit the same exhibits, slowly, from different angles, without ever needing to escalate. Let's do a slow replay of the primary rainbow, but even simpler than before. Sun behind you, rain in front. 42 degrees, light enters water and bends. The colours separate a little. Light reflects once inside, light leaves water and bends again. Many rays prefer nearly the same outgoing direction. That direction becomes bright. Your eyes collect those outgoing rays and interpret them as an arc, and your brain does the rest quietly, without effort. Now the secondary rainbow in the same calm shorthand. 2 reflections, fainter bow, reversed colours, a brighter region inside the primary, a brighter region outside the secondary, and a darker band between because fewer rays go there. A gentle stripe of physics, named and noticed centuries ago. Now the halo family in the same shorthand. Ice crystals, hexagonal prisms, 22 degrees, minimum deviation. Rays cluster near that angle. A ring appears around the sun or moon, sometimes with a warm inner edge. If crystals align, bright spots form. Sundogs. And if reflections dominate, vertical smears appear. Pillars. That is the whole case file. The rest is simply learning to rest inside it. Now, we can drift into a longer series of slow sky scenes, each one anchored to one phenomenon, then gently blending into the next. A morning with high, thin cloud. The light is cool, the sun is still low, and the sky looks washed with pale blue. You hide the sun behind a rooftop line, and the ring reveals itself as a faint halo, 22 degrees out. At first, it looks like nothing. Then you see it as a brightness change, a circular gradient. Then you notice the inner rim has a warmer tone. Then you stop trying to see it, and it becomes obvious. The cloud is full of tiny prisms. They are turning, tumbling, drifting. Each one refracts a tiny fraction of sunlight, and the air, for a while, becomes a slow optical instrument. As the minutes pass, a bright spot appears to the left of the sun, then a matching one to the right. Sundogs, steady and calm, a clue that plates have aligned, faces almost horizontal, falling like quiet confetti. The sun climbs a little, the spots soften, the ring remains. Your eyes do not need to track the sun's motion because the geometry tracks it for you. Now we shift to late afternoon after a brief shower. The air is full of glittering droplets, small enough to hang for a moment. The sun is behind you again, and the ground is still wet. The anti-solar point sits quietly in front, and the bow forms around it like a compass arc. You notice red first, a warm outer band, then green and blue, then violet tucked inside. The bow does not reach down into the puddles. It stays in the sky because it is an angle, not a bridge. And if you walk forward, it stays the same distance away in the sense that matters, because the angle stays the same. The droplets serving your eyes simply change. For a moment, a second arc appears above, fainter, reversed in colour, a double rainbow created by 2 internal reflections, and the sky calmly showing you a second pathway. Between the boughs, a darker lane, Alexander's dark band, a place where fewer rays go, and so the background dims, the atmosphere doing quiet accounting with light. Now as the shower fully ends, the scene can slide back upwards. The lower air clears, thin high cloud returns, and a pillar begins to rise from the setting sun, like a vertical whisper. The pillar is not a beam fired into the sky, it is reflection. Many small mirrors, many small glints, each one slightly different in vertical angle because crystals wobble as they fall. The column is the sum of those glints. And if you keep the scene gentle, you can let the pillar become a kind of slow metronome, a steady line that holds the light in place while your thoughts drift. Nothing urgent, just geometry repeating, patiently. Now we can take an even quieter turn toward moonlight. On some nights, the moon is bright enough to make a halo. The ring can be 22 degrees again, centered on the moon, because the same ice crystals can refract moonlight as they refract sunlight. The colors are usually subdued because the light is dim and your night vision is less sensitive to color. Still, the ring can be striking. A pale circle, like a quiet boundary drawn around the moon. Sometimes there are faint hints of arcs, sometimes only the ring. And in cold air near the ground, there can be a moon pillar, a silver column. Moon pillars are especially calming because they look like something you could step into, even though they are only a pattern of reflection. The same tiny mirrors, the same gentle wobble, the same vertical smear of glints. Light behaving politely, without drama. If you want one more quiet classification tool, you can keep it very simple. If it is centered opposite the sun, it is in the rainbow family. If it is centered on the sun or moon, and it is about 22 degrees out, it is in the halo family. If it is very tight around the sun or moon, only a few degrees, it is likely a corona in the diffraction family. And if it is a vertical column, it is likely reflection making a pillar. That is enough to hold the whole catalogue, and now we can let the catalogue repeat slowly, in a way that makes it easier to sleep. Refraction first, a bend at a boundary, air to water, air to ice. Dispersion next, a gentle spread of colours, violet bending slightly more, red bending slightly less. Reflection last, a turn inside a droplet, a glint of a crystal face, a pillar written vertically, and then angles. Always angles. The sky does not paint randomly. It paints where the geometry asks it to paint. 42 degrees for the primary rainbow, around 50 to 53 degrees for the secondary rainbow, 22 degrees for the common halo and for sundogs, 46 degrees for the larger, rarer halo. If those numbers feel too sharp, you can let them blur. They are not an exam, they are just the sky's preferred distances, like familiar steps in a staircase you do not have to climb. Now, we can keep going with the same calm, by taking a longer tour through a few more subtle halo forms, without turning it into a lecture. Sometimes, above the sun, you see a bright arc that seems to touch the top of the 22-degree halo. That can be an upper tangent arc, often linked to column crystals with a preferred orientation. It curves like a soft wing, and as the sun rises, that arc can change shape because the geometry shifts with solar elevation. Sometimes, high overhead, you see a bright, rainbow-like smile with vivid colour. That can be the circumzenithal arc. It is often described as an upside-down rainbow because its concave side faces downward. It comes from refraction through plate crystals, and it appears when the sun is low enough for that path to work. There are also arcs that form below the sun or near it, and halos that look stretched. Each one is simply a different path through a different crystal orientation. The sky runs a simulation with whatever shapes it has available, and you see the patterns that the simulation makes bright. If you want a calming mental image for all halo phenomena, you can keep it very simple. A crystal is a prism. A prism selects angles. Angles gather into arcs. That is enough. And now we can slow even more by returning to one phenomenon and circling it gently, like walking around a sculpture in a quiet gallery. Let's walk around the 22-degree halo again. You hide the sun behind a roofline. Your gaze rests in the sky around it. The ring is not tight. It is broad and pale, and it may take a moment to notice. When you see it as a circle that does not care where you stand. It stays centered on the sun because it is centered on the incoming light direction. The ice is everywhere in that thin cloud, scattering and refracting, and the ring forms wherever the deviation angle reaches its clustering point. The inner rim can be slightly brighter. The outer part can fade. The sky inside the ring can feel subtly different from the sky outside it, and the whole thing feels like a quiet boundary between two regions of light. If you are still awake, we can drift back down into raindrops again, because the atmosphere loves repeating itself. A brief shower passes through at dusk. The sun is low and warm. The rain is not heavy, but it is thick enough to seed the air with droplets, and for a short time, the primary rainbow can appear with extra warmth in its red band. The colours are not separate lines. They blend, because dispersion is gentle, not violent. The sky does not slice the spectrum into stripes. It smears it into a smooth gradient. If the rain behind the bow is darker, the colours look brighter. Contrast matters. The bow is easiest to see when the background is dim. Another quiet partnership between physics and perception. And now, without any need to announce it, we can simply keep drifting through similar scenes, because repetition is the point. A pale halo around the moon. A faint pillar above a distant street lamp on a cold night. A soft rainbow dissolving as the rain stops. Sundogs appearing briefly and then fading as the crystal alignment shifts. Nothing in the sky holds still forever, but the laws do. Refraction keeps bending. Dispersion keeps spreading colour. Reflection keeps turning rays back, and angles keep deciding what becomes bright. So the phenomena come and go, but the mechanisms remain steady, like a quiet heartbeat under weather. If you want a final, very gentle anchor thought to fall asleep on, you can take this one. The sky is a laboratory with no walls. The instruments are water and ice. The experiment is sunlight, and the results are rings and arcs that appear whenever the conditions quietly line up. No urgency, no effort, just light doing what light does. And as you rest, we can let the last few minutes be almost entirely a slow recitation of the patterns, with plenty of space between them, like a calm checklist the mind can release. Primary rainbow, one internal reflection, red outside, about 42 degrees, secondary rainbow, two internal reflections, reversed colours, about 50 to 53 degrees. Alexander's dark band, fewer rays between bows, a dim lane in the sky, 22-degree halo, ice prisms, minimum deviation, sundogs, plate crystals aligning, bright spots left and right, light pillar, reflected glints, a vertical smear of light. And that's the whole quiet file. Sunlight in air, the optics of droplets and crystals, the sky doing careful geometry while you do something much easier. Rest, settle, let the patterns fade.